Let's talk about polar coordinates. Well, we're going to introduce a new system which is different from the rectangular system with X and Y, and we call it a polar system. Later on in calculus, you're going to learn about cylindrical coordinate system and also spherical coordinate system. Introduction. So far, we have been representing graphs of equations with using X and Y, which are representing points or their pairs in the rectangular coordinate system. X, a value on x-axis, y, a value on y-axis, and we have different points connecting the points and having the graphs in xy plane. In this section, we're going to talk about polar coordinate system. Well, to form the polar coordinate system in the plane, first we need to fix a point that we call the origin or the pole. So first we fix a pole or origin, and then we construct from the origin an initial ray, which is called the polar axis. So you have an origin and you have a horizontal line to the right-hand side, which we call the polar axis. It doesn't have X and Y. It has the pole, the origin, and the polar axis. Well, the end point P in the plane can be assigned polar coordinates denoted by R and theta. R and theta. R shows the directed distance and theta is the angle, directed angle counterclockwise. So when we are graphing points in polar coordinates, we have point P with first coordinate R and second coordinate theta. The first one represents the distance and the second one represents the angle, or the directed distance. Well, suppose you want to plug in some points here. Suppose you have point 2 and pi over 3. 2 shows the distance and pi over 3 is the angle. Take a look at this. You have the origin. You have your polar axis. Theta is pi over 3. And the directed distance is 2 units. The next point, 3 and negative pi over 6. Well, negative pi over 6 is a negative angle. The directed distance is 3. So from the origin, we rotate clockwise to get to the negative angle, negative pi over 6, and the distance is 3 units. Finally, another point, 3 and 11 pi over 6. Okay, 11 pi over 6. We know that 11 pi over 6 and negative pi over 6 are congruent. So, as you can see, here you have theta equals to 11 pi over 6. And the directed distance is 3. So this is the point represented in the polar coordinate system. As you can see, we don't have X and Y. Here we have R and theta. We have R and theta. This is a new world. This is a new coordinate system that we call polar coordinate system. As we saw in XY plane, we can graph different functions in X and Y. In this world, we can graph functions in R and theta. So, in rectangular coordinate system, we had X and Y. Unique representation for each point. Of course, if you have 1 and 2, it's different from 2 and 1, and so on. But in the polar coordinate system, it's not the same. It's not going to have unique representation. So what is the relation? R and theta plus 2 pi representing the same point. Well, another way to obtain multiple representations of a point is to use negative values for R. R and theta and negative R and theta plus pi also equivalent to each other. So far, what do we have? We have R and theta equals to R and theta plus minus 2n pi, or R and theta equals to, now you can multiply your distance, directed distance, by a negative number, and your angle is theta plus minus 2n plus 1 pi. So if a question asks you to find equivalent polar coordinates, you can say that, hey, as long as I have R and theta, I can copy down my R, my distance, and add or subtract 2n pi from the original angle and get equivalent points. Or I can multiply my distance by a negative sign and then add and subtract my angle by 2n plus 1, the odd coefficients of pi. Let's take a look at this example. Here you have a point 3 and negative 3 pi over 4. Well, can we find equivalent representation for this point in polar coordinates? Yes. What I can do, I can copy down my R and then add and subtract 2n pi to theta. So I copy down R, add and subtract 2 pi to the original angle, and I get 5 pi over 4. Or I might decide to multiply R by a negative sign. R by a negative sign is now negative 3. And I add or subtract my angle by odd multiples of pi, like 1 pi plus minus 1 pi. Here we can subtract by pi and we get negative 3 and negative 7 over 4. These are all representing the exact same point in the polar world. There is no difference between 3 and 5 pi over 4 and negative 3, negative 7 pi over 4, negative 3, and pi over 4. They are all representing the exact same value. So what's the relation between the polar coordinate system and rectangular coordinate system? Well, x is equal to r cosine theta, y is equal to r sine theta. Rectangular to polar, if you have x and y, you can find tangent of theta, which is y over x. So theta is inverse tangent of y over x. R squared is equal to x squared plus y squared. This is the conversion between polar to rectangular coordinate system and rectangular to polar coordinate system. Well, later on in calculus, you're going to learn about cylindrical coordinate system and also spherical coordinate system. One example for you. Convert square root of 3 and pi over 6 to rectangular coordinate system. It means that you have your r and theta, you're looking for your x and y. So since it's polar to rectangular, we're going to follow x equals to r cosine theta and y equals to r sine theta. So you have everything you need. R is square root of 3, theta is pi over 6. X is equal to square root of 3 times cosine of pi over 6, and y is r, which is square root of 3 times sine of pi over 6. Well, we plug them in, calculate sine and cosine, and the outcome is, well, my x is 3/2 and my y is square root of 3 divided by 2. In xy world, you have x and y. In polar form, in polar world, you have square root of 3 and pi over 6. Another one. Suppose you have a point in rectangular or Cartesian world and you want to convert them into polar form. Okay, which set of formulas should be used? To convert rectangular to polar, tangent of theta is y over x and r squared is x squared plus y squared. So we have our x, we have our y, we follow the formula. X is -1, y is 1. Tangent of theta is defined as y over x. Y is 1 divided by -1, which is -1. So theta is the inverse tangent of -1 or arctangent of -1. And then r is equal to square root of x squared plus y squared. Well, square root of -1 squared plus 1 squared is square root of 2. So your directed distance is square root of 2 and your directed angle is 3 pi over 4. Guys, note that your tangent is negative, your x is negative, your y is positive. So it is in the second quadrant. That's how we convert a rectangular coordinate into polar coordinate. In many cases, you have equations written in polar form and you can convert them all back into x, y coordinate system. Some other times, the conversion is very hard. So it means that we have to graph the polar equation ourselves. So let us try. Our first attempt is to try to convert r equals to 2 into x, y. Well, by definition, x squared plus y squared is equal to r squared. We know that. At the same time, we know r is equal to 2. So r is equal to 2, r squared is 4. So what do we have? We have x squared plus y squared equals to 4. So this is an equation in x and y. We already know this equation. This is the equation of a circle. centered at the origin with radius 2. So r equals to 2 in polar world represents a circle with radius 2 in xy plane. Let us take a look at the graph. So suppose you're graphing r equals to 2 in polar world. So if your z is not 0, this equation represents a cylinder. If z is equal to 0, it means that we are moving out of the space into the plane. So the slice of this cylinder is just a circle. The circle centered at the origin with radius 2. You can Google polar graphs or polar grapher. Using Desmos, GeoGebra, and other websites, you can check it every day. We get different free websites helping us to graph different polar coordinate equations. Well, if you just go to Desmos, you have a lot of different polar equations. Polar equation r equals to 1, polar equation r equals to 2, polar equation r equals to 3, polar equation r equals to 4, r equals to 5, r equals to 6, another polar equation r equals to 3 minus 3 cosine theta, and many more. We can alter and change these functions. R equals to cosine theta. As you can see, it changes the polar coordinate and the graph. R equals to 1, and then here r equals to cosine theta, 2 cosine theta, negative 2 cosine theta, and the rest of them. How do we graph these using paper and pencil? Well, you have to plug in different points. By plugging different points and plotting them in x using r and theta, you don't need any x and y anymore. You just plug different points and then connect them together to have the graph of your polar equation. So our first attempt is to convert this polar equation into rectangular equation. If that gives us a common or something that we saw before, like a quadratic function or a linear function, or in this case, a circle, we quickly graph it. Otherwise, we have to plot polar points, connect them together to get the graph of the polar coordinate equation. Well, let's take a look at theta equals to pi over 3. Theta equals to pi over 3, we need to convert that into x and y. But what's the relation between theta and x and y? We know that tangent of theta is equal to y divided by x. So y divided by x is equal to tangent of pi over 3. Y divided by x is equal to tangent of pi over 3. So y divided by x is equal to square root of 3. So y is square root of 3 times x. We all from algebra know that this is equation of a line. It's an increasing line. Y equals to square root of 3 times x is an increasing line. So in polar world, you have this crazy looking equation. Theta is pi over 3. But in rectangular equation, we already saw many lines like this. y equals to square root of 3 times x. We already know how to graph these types of lines. So in polar world, you have this equation. Equivalently, in xy plane, you have this equation. If we go back to our Desmos or any other websites that we're using, here you can write down r equals to theta divided by 6 over divided by 3. Let me erase the rest of these. Theta equals to pi over 3. Okay, it says you cannot graph theta as an equation. Okay, let's see what we get here. Doesn't work properly, that's fine. Okay, this all gives r in terms of theta. It doesn't define theta separately. That's fine. Let's see, do we have anything here from, all of these are written as r equals to, okay. So it's better to use our conversion as we saw in the note and graph this as a line. And finally, we have r equals to secant theta. Well, r is equal to secant theta in polar world. How do we convert that into an equation in xy plane? So secant is 1 over cosine. R is equal to 1 over cosine. So r times cosine is equal to 1. But r times cosine, we already know it is equal to x. This is the conversion that we use. Take a look at the conversion that you memorize. X is r cosine theta. Wherever we see r cosine theta, we can substitute that by x. So here we have r times cosine theta, which is x, equals to 1. Okay, x equals to 1. Well, we already know that this is a vertical line. X equals to 1 is the same as r equals to secant theta. R equals to secant theta. So let's write this guy down here. Secant theta. As you can see here, you have a vertical line passing through 1. In polar world, it is r equals to secant theta. And in rectangular world, it is x equals to 1. Different methods, different ways, conversion between polar equation into rectangular equation and graphing them. Again, if you're interested in graphing r equals to secant theta directly, prepare to spend 1 hour graphing this equation. You need to plug in different values for theta and get different values for your r, plot the points in polar world, at least 10 points, and then connect them together to see the shape of this equation in polar world.